If you've been tracking the latest papers on sequence modeling, you've probably noticed a quiet but serious shift happening under the hood. Transformers have dominated the field for years, but they're running into a fundamental wall. And the research community is actively building the ladder to get over it. Let's talk about why attention, as brilliant as it is, hits a hard scaling limit, and how state space models are emerging as a genuinely different approach to processing sequences. The core issue with attention is quadratic complexity. When you compute self-attention, every token in a sequence needs to attend to every other token. Double the sequence length, and you don't just double the compute. You quadruple it. That's O of n squared. For long context applications, this becomes a memory and compute bottleneck that hardware can't easily outpace. The model doesn't just get slower. It gets fundamentally harder to train and deploy at scale. State space models offer a different path. They don't come from machine learning. They come from classical control theory and signal processing. In that framework, a system's behavior is described by a set of differential equations that map an input signal to an output signal over time. The system maintains an internal state that summarizes everything it has seen so far. When a new input arrives, the state updates, and the model produces an output. The key insight is that this update can be done in constant time per step. Linear scaling, O of n. But early state space models struggled with sequence tasks because they treated the state transition as fixed. The way the system updated its memory didn't change based on what it was actually reading. In language or code, that's a problem. Some tokens carry critical context. Others are noise. You want the model to decide, dynamically, what to remember and what to forget. That's where the selective state space model, popularized by Mamba, breaks the deadlock. It makes the state transition parameters input-dependent. Instead of fixed matrices, the model learns how to project the current input into a new state transition matrix, an input projection matrix, and an output projection matrix. This is often called the selective scan. The model literally tunes its own internal dynamics based on the data flowing through it. Under the hood, this starts in continuous time. You have a hidden state that evolves according to a differential equation. But neural networks operate in discrete steps, so you have to discretize that continuous equation. Most implementations use zero-order hold discretization, which essentially samples the continuous signal at fixed intervals and holds the value constant between steps. This gives you a discrete time state space model that can be unrolled like a recurrent neural network, but with the stability and expressiveness of the continuous formulation. The selective mechanism adds a third parameter, usually called delta, which acts as a learnable time step or gating signal. Delta controls how aggressively the model updates its state at each step. It can effectively skip irrelevant tokens, compress long passages of redundant text, or zoom in on critical transitions. This is why selective state space models handle long context windows so efficiently. They don't pay attention to everything. They selectively propagate the state only where it matters. Training these models, however, introduces a hardware reality check. Recurrence is inherently sequential. You can't compute step 3 until step 2 is done. That's terrible for GPUs, which thrive on massive parallelism. The solution is a parallel scan algorithm, specifically a prefix-sum approach, that computes the recurrence in logarithmic time across the sequence. It's mathematically equivalent to the sequential update, but it runs in parallel on the hardware. The catch is that parallel scan requires more memory and careful kernel optimization to avoid bottlenecks. That's why Mamba's authors spent significant effort on hardware-aware implementation details, not just the math. So where does this leave us in the research landscape? Selective state space models aren't a magic bullet. They excel at long context modeling and efficient inference, but they still lag behind attention on tasks that require dense, bidirectional reasoning over short sequences. Parallel training can also be less stable than attention's fully parallelizable structure. The current wave of research is focused on hybrid architectures, where state space models handle long-range dependencies and attention handles local structure. There's also active work on better discretization schemes, improved parallel scan kernels, and ways to make the selective mechanism more stable during pre-training. This isn't about replacing transformers. It's about expanding the toolkit. Sequence modeling is no longer a one-size-fits-all problem. Different architectures have different inductive biases, different scaling laws, and different hardware footprints. The models that win in the next few years will likely be hybrid, adaptive, and explicitly designed for the compute realities of modern accelerators. If you want to dig into the actual math, the technical reports break down the discretization process, the selective scan derivation, and the parallel prefix-sum implementation in full detail. The open-source implementations are also well documented, and running ablations on the delta parameter or the state dimension gives you a very clear picture of how these models actually behave under the hood. The field is moving fast. The bottleneck isn't just more parameters anymore. It's how efficiently we can move information through a sequence. State space models are showing us that linear scaling isn't a compromise. It's a different design space entirely. And the research coming out of it is going to shape how we build, train, and deploy sequence models for years to come.